Okay, so today we're going to talk about special IPv6 addresses, and well, it's just one of those days you might want to have some coffee. And so we're going to get into this a little bit. We talked about uh, the rules last time to uh, shorten IPv6 addresses and how they were formed. Um, I didn't really talk about the history of IPv6. Basically, IPv4 address space, they just started running out because there were an exponential increase in devices, and so we needed more addresses. And was it overkill going from a 32-bit address to a 128? I don't know. Maybe. That's a question that I guess maybe we can answer in 2100. We can make that decision after we've been running IPv6 protocol for a good 50 years, 50, 60 years uh, completely. I think once IPv4 eventually dies, and it will eventually go away, it's just going to be a little bit. Mainly because we have there's so many different uses for V4. It will eventually go away. I do see that there will just be a day when we just won't need it anymore. So, but for right now, we learn both, and the more you learn, the more you get exposed to IPv6, the less intimidating it is. Um, so I'm gonna go right to just a quick review on our V6 stuff, and just remember that we have it's it's sometimes I like to really think about what we're looking at. An idea here is that we have 128 bits that we work with. So I'm just gonna pull this up, and I don't know, I made several different notes here, so we can probably disregard those, but I'll use those later on. Just remember that our IPv4 addresses uh, is 32 bits. Each octet has 8 bits. Um, our IPv6 address is composed of hextets instead of octets, and that is actually, in this case, 32 bits. And then we have 4 of those. So just to look at that address and go, oh, okay, there's a lot of addresses there. 128 bits, 384 undecillion addresses in the space. We don't use that format to do it. We do it in terms of there's 64 bits. I don't know why that didn't work. And then here's our other 64 bits. So we have essentially 128 bits um, of addresses, and that's the way our address is formatted. Now, keep in mind, if I have I just want to kind of show you the extent of this, and we'll get into this along the lines of when we look at link local addressing and look at some different kinds. But the subnets are just extremely large, and it's it still happens is when we move a bit over. When we move a bit over, the we double the amount of uh, networks that are available in a particular subnet. It's just the same as our IPv4. It's just more information. So a couple of different types of addresses. In our IPv4 address space, we just pretty much have routable addresses, and we have addresses that are not routable or internal. But in IPv6, we have a lot of other different kinds because the address space is so large. We can have plenty of room to do certain things. So the differences in these addresses are going to be based on how you use them. So I'm going to go over a couple of different types of addresses. Some of these you've already seen. This is the first one is a link local, and a link local is kind of like a LAN address. If I just gave everybody a LAN address and said, okay, you can communicate on the local segment. So it's participatory, but routers do not forward link local packets. It's kind of like private addresses, but it's more like just links. So even with the private address of 192.168.1.0 or 172.16.0 or 10.0.0.0, those private addresses, routers don't forward them. We can still make networks out of them. These particular link local addresses have a very specific address space, and I'll show you that. Then we have a very special thing that's called a local unique address, and it is globally unique. And it's globally unique with the caveat. I guess the possibility does exist that we could have an address that is not globally unique, but it's very rare that would happen. So this global unique address, we'll go over the process of that. And then we have a global unicast address, and that's the way that I would actually route traffic between devices. My local unique addresses are more like how I would number my whole network inside inside devices. And global unicast routing would be how I would route between networks. And then I have this other special type of addresses, the documentation address, which is the one you see a lot of times. It's the one that looks like 2001 DB8. That is the documentation address. And then we have two different kinds of DHCP addresses. And I'll go over what those are. Now, these particular addresses are all going to be utilized in different ways. I need them for different reasons. And lastly, we'll look at some commands that we're going to use to actually turn these on. But I want to go back and look at specifically the link local address. Now, link local is, again, not forwarded by a router, and it's always using the FE80 10. So we're going to look at link local here a little bit, and we're going to think about the way that works. So I'm going to kind of take you through this. I'm using my computer here in my home office, so it looks a little bit different than what I would do at school. I want to make sure that I have everything in the right frame here. Link local. What I'm going to do is I'm going to basically assign a prefix for link local. I would give my router a command to create that prefix, and it's unique on a link. So if I have let's just say that I have a router and I have turned on link local addressing. Now, any device that I have connected on that particular link could also have IPv6 addressing, and I would just number them. I mean, whatever I want. It's notice that this is FE80, and that's to 10. So I'm just going to show you this. If I convert this into binary, all right, there's my 10 bits for my prefix, and then the rest of the bits, all 128 of them, in this case, here's my prefix, right? These 10 bits. Now the rest of these bits and I can keep going all the way to 128. And so if I put a 1 there, right, then I end up with FE80 1/10. That would be the first address on my link, and then my computer on the other end, or my device on the other end, would be able to communicate on that link, and it would have its own address. So I could assign those if I wanted to manually, but link local, they are automatically created. So they're not forwarded by a router, but they allow devices to communicate on link. So in this case, my network should converge with IPv6 turned on if there is a link local address defined on the interface of the router. Okay. And it always uses FE80 with 10 as the prefix. Okay, the next thing that happens is a local unique address, and this actually is a lot more closer representation to private addressing, and there is a process by which we create local unique addresses. Now, I say global. They're called local unique because they're unique addresses that are locally assigned, but they actually can be globally unique. And the reason why is because they're assigned using a random process. It doesn't work like DHCP. It's not where I assign an address out of a pool, which is what DHCP does. But I actually use a randomized process to create that local unique identifier. And I want you to imagine something. Imagine that I had a car company, and it was Ford Motor Company. And I went through and numbered my global network of network resources. In this case, maybe I had computing resources on 4 continents. And I numbered all my devices with a random process, and everything had a unique address. And Tesla did the same thing. So let's say they're on 2 continents, and they renumbered all their networks with their globally unique but locally assigned addresses. And so we have this very massive network that is assigned. If we were using IPv4 and we had used some local addresses, and let's say that because we were really big, we had gone ahead and used a 10.0.0.0 subnet. And we had assigned everything under our purvey IP addresses in that subnet. And we could cut it up however we want to, it doesn't matter. but we start assigning addresses out of that big bucket of 10.0.0.0. And then we do the same thing at the other company. But what happens when Tesla Motors purchases Ford Motor Company and we have to combine those networks? What we end up doing is we have two networks that are numbered with 10.0.0.0 addresses. And so when we try to merge those networks, it's a very difficult process and it causes a lot of headache. We have to renumber everything. And you say, well, DHCP could resolve that issue. Well, not really. DHCP is not going to be a resolution there because we're going to issue addresses out of a pool. But what does work is a global ID or a locally assigned globally unique IP addresses. Because they are used pseudo-randomly, if I were to create these networks of addresses and Ford had one set and Tesla had another, I could merge these two networks. It would almost be a cakewalk to do it. So I'm going to show you what that looks like, and we're going to kind of look at this. Okay, so if I have they're called local unicast, locally assigned unique addresses, I use a pseudo-random process. Now, what the standard says is that I'm going to utilize my first 7 bits, and it's going to be FC00. Now, what it also says here, and that's in the prefix, and I'll show you that. This is the way that this works out. If I have F, and then I have C, which is 12. Okay, all right, that's F, and then this first bit represents 8, and the second bit represents 4. That's 12. And then I have another bit right here. Okay, and then I have this one bit that has to be set when I assign the address locally, and that's just part of the specification. So once I assign that particular address locally and I set that bit to a 1, what I end up having is FD, because that becomes a 13, 0, 0. And so what I'm doing is I'm using this prefix. Now, notice how that FC00/7 became FD00/8. My specification said on my 8th bit I need to make it a 1, right? And so that's exactly how that turned over. Okay, what I do is once I have these 8 bits right here, I create what's called a global ID, when that's 40 bits. When I combine it with the prefix, that's 48 bits. And then I have a subnet, which is 16 bits. This is the first half of my address, of my 128-bit address. All right, this is let's put a star here. Okay, so here's my first half, and then I'm going to go ahead and put a pipe symbol right there. There's my second half. Okay. So this is my essentially my actual prefix that I use in my address, and this is the interface. So I'm going to show how you make each one of these. The global identifier, this is where the random process comes in, and I'm going to go and basically I'm going to take a timestamp. So it's going to be the time combined with the actual interface ID. It goes through a hash, so it creates a secure hashing algorithm, and then they take the least significant 40 bits of that result, and they create this value that's attached on it. So it is, when it's pseudo random, it is actually a very random, because that timestamp is going to make that hash completely different every time. Okay, so that gets on there, and then the subnet is something I can define at the site. I would figure out whatever this 16-bit subnet is. Now remember, in an IPv6 address, a subnet, this 16-bit subnet, is just going to be an octet. So I might define my local subnet at my site to be, well, whatever I want, 000A, right? I could do that, or I could do 0001, and I could just increment it up. But let's say I was a large organization, and I had created this global ID that was pseudo-random, okay? And then I have a local site here. How many different actual physical locations could I have and still be unique, right? So notice that is, we'll just look at that. If that's a hexadecimal number, right, and it could be represented by 256 times 256, right? FFFF. So that gives me 65,536 actual networks just right here that I could create using, with all this first 48 bits being a random number, and then I can dole out these for each particular local network that I wanted, and then every device that's attached to that network is going to get this special value that's 64 bits. And we'll use this value called an EUI 64. I'll show you how to calculate that, and we will use that in a number of different ways and cases. So this will come in pretty handy, and it just attaches on to the end of that. And so we have these IPv6 addresses that are actually relatively easy to create, and they're globally unique. So if I were to number my entire network with that, I would be able to essentially route traffic and be unique in doing it. Now, there is another address. I don't know if talked about it, but the next one is a documentation. So in all of the addresses that you will see printed in the material and in the text and other things, and actually all the IPv6 addresses that you will see anywhere printed or in networks will begin with 2001. And that is the documentation address. And so I'll show you in the RFC if it shows that there are several RFCs that are there for IPv6, and you can read all about it. But the documentation address is just 2001 DB8, and oh, it actually shows it right here. Let's see, yeah, 2001 DB8. Notice it's a /32, so the first set is 16 bits, the second set's 16 bits. Notice there's a leading 0 right there that's been taken out, so it would be 2001 0 DB8. That would give us 32-bit address. This is just a documentation. It's just whatever we need one, we can do whatever we want as long as we use 2001 DB8. It's not routable ever. It's documentation. Okay. Oh, I didn't even have that on the screen. I'm sorry. Let me show it again here. Let's see. So here is I have a recording window that tells me where my recorder is actually at. So here's the 2001 0DB8 address that's listed just for documentation. Okay. All right, and these are all the different kinds. So this here is that unique local address, and this one is the link local. So that is link local. Okay. Link local is not forwarded by a router. Unique locals can be. They're not forwarded, but they are they're used to number those network resources. Okay, and they're globally unique. All right. Let me look here. Okay. So let me get back to the EUI, and this is the extended interface identifier. 64 indicates that it's a 64-bit address. So we often use this EUI 64 to tack it on to the end of the IPv6 address whenever we want something to be auto-configured for us, and it saves a lot of time. It's definitely a good thing to understand how this is generated. So I want to show you a couple different things. I've gone through and I've actually pulled some MAC addresses and I've randomized them. Notice that this is what a MAC address in a Cisco device, when I do an interface or I look at an interface and it shows me the MAC address, it's going to show me this MAC address in this format. So I have these values here, 6 bytes. So MAC addresses are always 6 bytes. Now, what we know about 6 bytes is that if we look at that in terms of bits, this is 8 bits, 16 bits. This is another 16 bits, it's 32. And this is another 16 bits, it's 48 bits. So a MAC address is 48 bits. I noticed that when Windows gives us the MAC address, it does it a little bit differently. It just separates each byte with a colon. And this is merely a formatting. So when you see these two addresses given, and it's the same thing, it's just formatting. But these are 48 bits. Okay? What I have to do is I have to come up with a way to generate a 64-bit address. Now, here's the catch. That what happens is this particular OUI that is on the first half of the MAC address is manufacturer specific. Okay, and the last half of the IP address is interface specific. Well, what we want to do is we actually have to turn this 48-bit address into a 64-bit address. And so one of the things that happened is they actually created this method, and this is the EUI64. As we take this MAC address right here. So I'm going to paste it, and I insert FFFE into the middle of it. The other thing that I do in order to change this globally unique identifier that would be the MAC address into something that's a little bit different, because I don't want anything to get confused if I start chopping up numbers, right? And I'm going to go ahead and I'm going to flip this 7th bit. So what happens is, if I look at this 00 in terms of bitwise, and I'm going to turn that over to a 1. Now notice that's the bit that represents 2. So if I were to write this again with my 2nd bit flipped, with my 7th bit flipped, that 0 is going to become a 2. And the final thing that I do here is I take these colons out. And I'm left with a 64-bit segment that I can stick on the end of my prefix. And this should be unique for any interface that has a MAC address. Now, if I have a router interface, like a serial interface that doesn't have a MAC address, what will happen is the lowest MAC address that's in use on the router will be utilized to create this EUI64 address. So this is my EUI64 right here, and so one thing I'll show you is another way to think about how to do this in a kind of a quick second. So I'm going to go ahead and write out okay. So this is just a quick way. I wrote out my hex values. Now, whenever I have, and I'm gonna use this other MAC address right here. We can, let's see. Let me go generate one here. Okay. I have a tool that I generated a MAC address, and I'm just going to generate one randomly, and I'm going to put it in this Cisco format. Okay. So here's my MAC address. Now I'm going to go through that EUI formation. Now, my first bit is an A. Now it's going to stay. It's going to stay. But my second value is a D. Now, one of the reasons why I wrote this in this way is because whenever I Now, let's see. Let me show you if I can show you this. It's these two values right here. When I flip that 7th bit, if I am on a 3 and I flip the 7th bit, it's going to be a 1. If I'm on a 0 and I flip the 7th bit, it's going to be a 2. If I'm on a 9 and I flip the 7th bit, I'm going to end up with a B. If I'm on a B and I flip the 7th bit, I'm going to end up with a 9. Right, so that's just a way to think about this. So if I have a D as my second number, I'm going to end up with an F right here, right? And I'll show you that a little bit more closely in a minute. So I'm going to go ahead and convert this into my EUI64 format, FF, FE, 37, no, sorry, FF, FE, E3, 37D3. Okay, there's my EUI64 format. Notice I just stuck the FFFE into the middle. I kind of did it fast. We'll go ahead and do one more. I'm going to generate a MAC address. But I'm going to use this other format here. Okay, so I'm going to flip the 7th bit. Now, in this case, and I'm going to do the binary again, okay? In this case, my first number, 9, looks like this. And then I have an E. An E, we know, is 14. 8, 9, 10, 11, 12, 13, 14. Okay, now when I take this 7th bit, now my first one's going to stay the same. It's going to be a 9. I'm going to flip my 7th bit, and I'm going to get an 1100. Okay, it's 1100, which is really a 12. In the case of that being a 12, that is a C. So originally it was an E. Now notice that it's a C right here. Right? So you see this, I'm using these two values to flip. That's just a shorthand way to think about it. If I want to write these numbers out, and I can write them just like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So my second digit is an E because I flipped that 7th bit. 1, 2, 3, 4, 5, 6, 7. I flipped it, and now I'm at a C. So 9C, 5B, and then I'm going to insert the EUI identifier in there, which is FF, FE. I don't know why they chose FFFE, other than the fact is that when you look at it, that's FF, and that's FE. Other than the fact that it's just a sequence of binary digits that can be error corrected, possibly. But so here's my 9C, 5, 8, 6C, FF, FE, and I got to remember to insert that FFFE right in the middle, and then my F5, A5. This is again my EUI64 identifier, and that's the way it works. And it's once you get the hang of how to do it, it is a very straightforward process. But we're going to use this anytime we, in the case of generating this this identifier um, local address, or if we're going to use an auto configured DHCP address, which is the next type of address. So we have two different kinds of DHCPs. Um, DHCP is where I would, in general, in IPv4, I would actually give the addresses out in a pool. So I would set up a pool of addresses and I would just hand them out as the requests come in. But I decided that what I would, they would, because I would do these two different ways, um, is I would actually use the DHCP server in one case to just give me the prefix of the network, and I'll configure it, and then I can create the address. I can get the address from the server, or I can use autoconfig, which will allow the DHCP server to tell me the prefix length and the address prefix, and then use EUI64 process to actually create the other half of the address. It makes it easier, especially if I were. Let's think about a cellular network with millions of devices, and technically I could just have uh, a handful of DHCP servers that handle my whole network. All I have to do is tell it what its prefix length is. The device itself will create the EUI64 address for the other half of the interface. It's very straightforward. Once you figure out how it's done, and you get that you get that down. And again, here's how we do it: we take the MAC address, we split it in the middle, we insert FFFE, and we flip that 7th bit. That's this other side, and that can be done by any algorithm, anywhere actually. Anything that has access to the MAC address on the device can do that. So here's just going over real quick the commands and kind of the differences when we're in a router. So this is where we're going to actually specify the whole address. If I want to go ahead and manually configure my router interface to use IPv6, and I want to tell it this is the address that you're going to use, I'm going to do it this way, right? I'm going to use the IPv6 address, and then I'm going to actually put the address and then a slash prefix. So this is where I would utilize that prefix length, which in our IPv4 world is this CIDR notation, but in the IPv6 world we call it the prefix length. And then if I want to tell the interface that it's going to create link we're going to give it link local addresses. Remember, that's that FE80 address. I can define whatever prefix length I want here as long as it's greater than 10. So I could create the FE80 / 12 if I want to, or 14 or any number, and as long as the router knows that it's a link local, it's gonna create and think about these packets as if they were link local packets. It's not going to forward them, and it's going to be it's going to know that FE80 prefix is for link local. And then of course we could use the EUI64 method to generate a locally generated or globally unique address. So that's the EUI64 right there, indicating that we're going to use that address. We're going to use the prefix, and then we're going to use the method we just talked about to create that last half, the interface. And then we have our DHCP commands here. The most common is the DHCP autoconfig. My DHCP server doesn't have to do a lot of work there. It just determines the prefix and the prefix length. So that is IPv6 in a nutshell. I definitely would recommend reading the material, but hopefully after watching this and you have either generated a list of questions that you want to ask, and if you have some questions, I definitely want to answer them. So I encourage you to ask questions. And then the other thing is to go through and look through the material. Maybe it will not seem so foreign to you. It's a little bit to process at first, but when you start taking these things piece by piece, and realizing that IPv6 address space is huge. It's humongous. It is absolutely humongous. I read somewhere that IPv6 is enough addresses for every grain of sand on the entire Earth to have its own subnet. I'm not sure how big it is, but it's there's a lot of addresses there. So that's IPv6, and we'll definitely go over this more, and we'll talk about it. I want you to remember this method for remembering how to flip the bit. Definitely remember that the Cisco format and the Windows format of the MAC addresses are the same. Remember FD/8 for the global, and the word pseudo-random, right? That we're going to randomly generate this information. In this case, these 40 bits. And then a link local FE80 with a prefix length of 10. Okay. We don't say /10 as a shortcut. We just say FE80. Well, we could. I guess we could say /. I don't know. Not too many people work with IPv6 all the time, so I guess we're constantly forming that. You can say /10 if you want to, but I would generally say the prefix length 10, and when I say that, to make sure you are aware of it. But again, if you have any questions, feel free to let me know. Thank you very much.